Hello. Welcome, everyone, to my talk, Familiar Tools in Unknown Territory, Exploring GenAI with SpringAI and Testcontainers. I hope you had a good lunch break. Now you can sit here a little bit, relax, and listen to all the AI content I'm going to present to you. And we are all kind of faced with the current AI wave, and sometimes it's better to ride the wave than like getting drowned by it. And to a certain degree, that's also what I'm doing, what I'm here to talk to you about, like how you can maybe try to ride the AI wave than just getting swamped and drowned by it. And I hope you will get after this talk a feel how using familiar tools you are all using in your day-to-day jobs in the Java technological ecosystem, tools like Spring, tools like test containers to just get better hands-on experience on AI development. Maybe a quick show of hands. Who of you is already doing GenAI development, agentic development, something like this in their professional context? Yeah, so thumb. And who of you have been like asked to explore these topics as a research capability or something like this in your professional context? Okay, not that many, and that's always what I notice when speaking with people, with professionals in the industry. The hype and the buzz is very loud in certain echo chambers, in certain Twitter echo chambers, but the reality is it doesn't necessarily touch the life of day-to-day software development, at least not yet. My name is Wittek. I'm working at Docker as an engineering manager. Before I was part of a startup, Atomic Jar, that was a startup behind developing and supporting the open source library Testcontainers. We got acquired by Docker. Then I was doing continued to do some test container stuff at Docker, and then they put me on this super important AI project, so that's why I'm now talking to you about AI stuff. But of course, test containers will also play a role in my talk. And I'm not a deeply AI person, but like maybe many of you also, I ended up having to deal with this AI wave, having to find my own space within this new emerging domain. And I did some AI stuff in the past, but that was like so different, right? I did with my wife a paper using deep learning, and that was for classifying pigeon behavior, like pigeon, the birds, and using deep learning to classify in a video stream what a pigeon was doing. Was it eating? Was it walking? And so on. And it's interesting. I cannot transfer any of this former domain knowledge in the current AI domain as we see it right now. That may be something good, right? Even if you haven't been very deeply immersed in the machine learning, deep learning ecosystem, it's basically a reboot what we see right now with LLMs, because many of the things, how we work, how we integrate with them, just feel fundamentally different. So it's really not too late to start and become a domain expert yourself. I was asked to share the Slido link. You can already join it. I will also share it again at the end of my slides, where you can put your questions and then we will answer them at the end. Hopefully we will have some time for this. Okay, let's look at the current state of the hype cycle for AI, and that's from 24, so there is not a 25 version yet. I think it would look very different or like slightly different, but so we see but it's very high AI engineering. That probably means something like GenAI development, what people call GenAI development, and we already see last year raising the stuff like multi-agentic systems. That is something that's probably right now at the peak, right? Agentic software development is very much at the peak. Something like MCP is not even part of it, and that's like another hypey buzzword that we will also look a little bit at it. So very much what we see right now, it feels like we are somewhere at the peak, before the peak. So I guess we should expect not that far in the future many of the things that are now pushed a lot into the narratives to slowly drop into this trough of disillusionment. So people will see like, oh no, there are actually limits to what we can achieve by integrating LLM components into our applications. But then hopefully we will start our slow climb towards the plateau of productivity. And then I think it will be more, play a bigger part in our normal day-to-day lives as software developers. So I said a lot of the former traditional machine learning, deep learning domain knowledge not necessarily applies anymore, or is not really a requirement anymore for getting immersed in the current LLM wave. And how did this actually started to happen? So LLMs, large language models, it's relatively new, right? It has been kickstarted by a academic research effort by Google, and that was the paper "Attention is All You Need." And this paper was talking about the transformer architecture of these large language models, which is just a core of their implementation of their architecture, and most LLMs are based on these computer scientific theoretical concepts. And it didn't have a big impact on the overall industry yet, right? So we had already OpenAI back then, and they were implementing the different GPT variants that were usable through the OpenAI APIs, but not many people started doing it before 2020. So it became only really visible also in the consciousness of society and the software industry when ChatGPT appeared, which is then a UI to interact with such an LLM. And then we suddenly saw the potential and the capabilities those LLMs might have, just because the UI, UX was so accessible to everyone, right? So it was accessible to us as technical people. It was also accessible to non-technical people. Like, everyone can use basically this chat interface. And that, in my opinion, then triggered this wave. And then another very important thing then started to happen when all the big players had to compete against the mode that OpenAI initially created through their very capable GPT models that were all proprietary, of course, and effectively closed source. So the big players, in order to change the dynamics of the market, went ahead and released open models, open source models. Are they truly open source? There are a lot of discussions around, right? The Linux Foundation basically accepted those licenses of those models as open source licenses, but it's of course not necessarily fully open source as maybe free software advocates will talk about it. But either way, it means suddenly models became available, very capable models that everyone can run. Like, we can run on local machines if they are powerful enough. We can run on-premise in our own data centers if our servers are powerful enough. And the famous examples here are the Llama families that come from Facebook or Meta. We have Mistral, that is our European success story, I would say. We have Phi from Microsoft. We have Gemma from Google, that is the foundation of their own cloud offering, which is called Gemini. But Gemma is the open model that is backing this. We have Qwen from Alibaba. They also made really good progress. And then, beginning of this year, DeepSeek from China suddenly made a big splash, because that was a first time there was an open model that you can run in your own premises that was able to really challenge the established players like the GPT-4 models, 4o models, and so on. And it suddenly showed that the market becomes very accessible. So the first movers, like OpenAI and so on, they don't necessarily have their mode anymore. They build up over years of research. No, it's now becomes a commodity. And that's very interesting, right? Once technology becomes a commodity, actually the industry shapes around it in different ways. People start to integrate it, build technologies on top of it. And that's what excites me about the current phase we are in, that we are in a phase where the LLM itself as a component becomes a commodity. So then we, as software developers, we don't have to be a machine learning expert. We just use those readily available commodities and build on top of them with our own software, with our business logic. That would then be the agentic software and so on. Okay, so what parts in general are involved when developing a GenAI application? That's how a layered architecture could look like, very simplified, but I think it can be often this case. And if you look at it, it's like very much like a traditional layered Spring Boot business application, right? You have some UI, you have a business logic core, then you have something that could be a middleware that takes a lot of dealing away all the details. Examples for these middlewares are something like SpringAI in the context of Spring, something like a library, then like LangChain for J. So they take away all the details of interacting with the GenAI related components. Then you, in general, interact against different LLM APIs through an OpenAI API. So the OpenAI API has become a de facto industry standard, and all the different cloud providers, inference providers, tend to offer their models behind this OpenAI API. And that makes it then also easy for like the middleware that you can, in theory, plug and play different models, LLM models, into your application. In theory. In practice, you likely can't, because you have to tune the rest of your application to how the model behaves and how you have to instruct the model. But at least like middlewares will give you this promise, right? The same way they always promised you can plug and play your databases, which we can in theory, but not in practice. Okay, and then for getting these usual chat completions, you interact with the inference API that then interacts with an inference model. If you want to do something like a RAG, Retrieval-Augmented Generation, so that is when you get your own data basically into the LLM, then you need an embeddings API. These are used for creating vectors from the input, and then use this vector to look into a database. Okay, what relevant documents do we have for this? So for this, another kind of model is generally used in embeddings models. These models are good in creating those vector representation of the input. And then, in case of building a RAG, Retrieval-Augmented Generation application, you also have a very traditional data access layer that is for storing your own specific data, and that can be something like a Postgres database with a vector extension, right? So you have your normal Spring Data JPA or whatever, and you just plug in a Postgres there. And then where do those models then run? Very often they run in the cloud. If you're just using OpenAI, they will run in the cloud. But nowadays you can use something like Ollama, you can use something like Docker Model Runner, what I will show later, and easily run those things also locally, with some implications we will see in the way how the models behave. But at least from the API compatibility, running locally is completely fine. Just the behavior of the model will likely be different, because every model behaves a bit different. How is now the request flow when a user makes an interaction with a GenAI application? That is now first the simplest, a chat example, right? So a user sends some chat request, the application receives it, he sends it, the application sends it to the LLM, normally through the OpenAI API, and then gets a response back. That is a very, very easy, normal example. Of every chat example you will find a tutorial, and that is completely stateless. So the LLMs itself are fully stateless. They even don't have history or memory about the chat context. If you want something like a context of the chat, so that the LLM can refer to previous questions and consider those in its answers, you need to implement this in your application layer yourself. And of course, those middlewares help you with it. So now, once this Retrieval-Augmented Generation comes into play, where you want to add your own data into the LLM, your application layer, as I said before, takes the input, sends it to an embedding API, gets a vector back, then, so that's the retrieval model, right? Then uses this vector to look up data in a potentially vector database, then takes this data, adds it to the original user request, and sends everything to the LLM. Why would you need to do this? Because the LLMs have a fixed knowledge window. They are trained to a specific date, 2024 or whatever, and the LLM will not know anything about your company-specific data, for example, right? So how do you get this in? In theory, you can like retrain the model, fine-tune a model to also contain your own information. That tends to not work well, because the model was already trained on so much public information. If you then add a little bit private information into it, tends to not really move the needle. So a strategy that then works very well is using this RAG architecture, where you just add information into the prompt by this Retrieval-Augmented Generation mechanism. Okay, and then something that nowadays you would call MCP integration, but traditionally called as tool calling. So what if your application needs to interact with external system, wants to get data from external system, sometimes even wants to maybe execute writes into external system? For this, you can hook tools into your GenAI application. And a very simple example of a tool could be an external service that gives you the current time. Because if you ask an LLM what the current time, the LLM cannot know, right? So what you would do, you would register this tool in your GenAI application, then the request comes in, the LLM will see like, oh, the user wants to know the current time. I don't know the time, but I know I have a tool registered that tells me the time. Then it tells back the application, call the tool for me. The application goes, calls the tool, takes the information of the tool, adds it to the context of the prompt of the user, gives it again to the LLM, and then the LLM says, oh, the user wants the current time. The time as given by the tool is XYZ. Okay, so I will answer with foobar. That's basically how then the tool calling works and how you then build agents, right? When you add tools, people nowadays tend to call these then agentic systems. Okay, and on a technical level, what happens when you call these model inference APIs? It's very, very simple. So the request itself looks very, very simple. So you interestingly tell with which model you want to interact. So the inference API doesn't represent a certain model running, right? Because it's a very ephemeral, stateless thing. You say, I'm sending a request to this inference API and I want to interact with model, in this case, GPT-4o, if you're calling OpenAI. And then you send your, you specify your role. So if you say here, role developer, that's a system prompt you add. So that is information the LLM will consider for tuning the answer on a certain way. And like you have all kind of cargo culture knowledge about how good system prompts look like, because no one really knows how the LLMs will internally deal with them. But that's what it is currently. And then you send your own actual payload through role user and say, okay, this is my prompt, hello. And then it will answer something back. For example, something like this. So it will give you metadata, which model was used, how long it took, how many tokens were used, and so on and so on. And then it will send you a couple of potential answers your application might then expose. These are in these choices area. And in this case, there is a message choice coming from an assistant. The LLM will always act as the assistant and just contains the content. And there are different kinds of message type. It's not really important to go here into these details, because when you're using those middlewares, those libraries, you're not dealing with this. You're just having some kind of client in your Java code and just calling whatever abstraction is provided to you. Okay, so yeah, if we are a Java developer, we're not going to like manually call those APIs ourselves, right? So what tools do I have at my disposal? I think SpringAI is a very, very good starting point. The other one would be LangChain4j. So if you're a Quarkus developer, LangChain4j is probably the better integrated variant you can get started. If you're already a Spring developer, start using SpringAI. It's like very Spring idiomatic in everything, and it makes the actual implementation code you have to do very, very minimal, because all these instrumentation we have seen in the one of the first slide about this request response flow, calling back sending back the information to the tool call to the LLM and so on. All this glue code is then taken care of already by this framework. And yeah, so it has like all the basic features you need when building an agentic LLM application. It has a super easy abstraction for building RACs. This is this retrieval functionality. It has a very, very easy mechanism to integrate tools yourself, and the memory is used if you want to have actually more persistent chat experience. And of course, nowadays it also has support for MCP. Who here has heard of MCP? Yeah, everyone. And who is already using MCP for something? Well, actually some people. Very good, right? So that is now the big thing. Everyone is jumping on this hype. We as Docker are jumping on this hype. Everyone has to play in this hype. And what is MCP? So I would describe MCP as a standardized mechanism to integrate tools into your GenAI application, right? So instead of before adding custom tools functionality, now someone can just provide you with an MCP server that gives you a certain endpoint, and then you connect this MCP server with the MCP client within your SpringAI application, and then all this tool calling, it kind of just magically happens. And now you can think of, if we provide MCP servers using good, useful APIs as a nice abstraction layer, then suddenly for my GenAI applications, all kind of information sources within my organization become accessible. So there is a Notion MCP server, if Notion is your wiki, so you plug it into your application. There is a Atlassian MCP server, which I always want to use, but I haven't yet wired it up in our own organization. So that would be so useful for me as a manager to manage the Jira tickets through an agent system, right? Instead of going to the Jira board itself and move cards around, which I don't like. And we see currently this ecosystem of MCP servers explode, basically, right? And the promise that you can plug them in as black box functionality to just magically enrich the data and the information on which your LLM, on which your GenAI application can act on. And let's see what will come of this. Because a big challenge of this right now that we also try to solve from the Docker side is security and access control. Because if those MCP servers then have a lot of a high degree of access to information or even the capability to write information, you can think about all kind of interesting attack vectors, how the LLM just acting or an agent system just acting unexpectedly can wreak havoc in your critical business data systems, I would say. Right, okay, so how do we wire this stuff up? Thankfully, using tools we already know, it's pretty easy, and it's like we don't have to introduce new stuff, right? So you basically can continue just using test containers for most of the things. And who of you here is already using test containers? Yes, that's many hands, and I like it, right? So test containers, Java library, but also library for other languages nowadays, open source, and it's just giving you basically a kind of like a Docker SDK for within your Java code. For example, your tests, but not necessarily only your tests, to start Docker containers programmatically with a lot of important convenient functions like waiting for a container to be then actually ready, not requiring fixed port mapping so you don't run into port conflicts and so on. So the goal for us behind test containers was always you can enter a new project. If you enter a new team, you clone the project, you can directly run it. You don't have to set up databases, you don't have to set up the Kafka and so on. Everything should be configured through your code, through your Java code using test containers. Okay, so the first example is like the basic one with Redis and the generic container API. And then when the whole AI wave happened, we started to also build an Ollama container. Because what is Ollama? Ollama is a convenient way to run LLMs locally. And normally you install Ollama natively and then it exposes a port, and then you can just, instead of pointing to a cloud OpenAI API, point to localhost 11434 and have your models running locally on your machine if your machine is powerful. And it worked quite well. But of course, once you introduce this, and that's not managed then by test containers, if now a new developer joins your team, they have to have expected to have Ollama already installed. They have to have all the right models already pulled. So from the test container side, we thought, that's not really nice. We want to also have a Ollama abstraction so that then Ollama runs in a container. And that started to introduce interesting problems because those LLM models, most of them tend to require GPU to be sufficiently fast. They can run on the CPU, but then it becomes a super slow experience. So you have to get the GPU access into the container. And how can you do it? So test containers already have an API, and like this code is what you need to do to mount a GPU into a container started by test containers. In case of the Ollama container module, we already do it for you, so you don't have to do it yourself. But that basically only works on Docker CE, meaning on Linux, and on WSL maybe with some caveats. On macOS this won't work. Why? It's a later slide that talks about this, so I will not come. Now it comes, right? So, okay. So if you're on Docker CE on Linux, you can just mount the GPU, be happy, run very fast, inference, everything good. So now on MacBook it doesn't work, and why? So what is the problem with MacBook and GPUs? Because the new Apple Silicon MacBooks have very, very capable GPUs, right? We want to use them to run fast local inference. So for technical reason, the situation we have here is specifically in the case of Docker is complicated. And I'm like just sharing openly the situation we are in. If you're using Docker Desktop on macOS, you are running containers in a Linux VM, Linux virtual machine. This Linux virtual machine is implemented using the Apple virtualization framework, which is their own built-in hypervisor capabilities. So this Linux virtual machine has no access to the Apple Silicon GPU, simply because this virtualization framework doesn't allow to mount GPU access into this VM. So now, already last year or earlier, we started to think, okay, how can we work around this limitation? So one start was Docker switched from using the Apple virtualization framework to using the hypervisor framework, which is a lower level hypervisor framework offered by Apple. And that feature is called Docker VMM. And if you use this, you can access this, toggle this in your Docker desktop installation since 435. If you use this, now a virtualized GPU becomes accessible in your Linux VM. And this can be accessed or interacted with through Vulkan APIs. So Vulkan is a GPU abstraction layer, vendor-independent abstraction layer, driven by AMD mostly, I think, but vendor-independent. So now in theory, you have access to it. In practice, most open source libraries that want to run inference or other machine learning workloads don't necessarily support those Vulkan APIs. So already, like, what does it bring you? You now can create an Olama container with GPU access, but they are not supporting Vulkan APIs, so they cannot use the GPU. Doesn't help you. Then we have a very, very weird different problem, and that has to do with that the kernel pages for the of the Apple Silicon operating system use 16K, but the virtualized libvulkan GPU device uses 4K kernel pages size. So they actually don't line up. So it just doesn't work. It just crashes. So you need specifically patched Mesa libraries within your container images. Also not very user-friendly. And then in addition, if you get everything lined up and working, you still pay a roughly 50% virtualization overhead. So at this point, you will say like, okay, why should I run then Olama in a container or inference workloads in a container? I can just run Olama natively on my Mac and have all the speed, and like, why bother with Docker in the first place then? So yeah, we realized this and like, okay, how could we solve it? How could we work around this? And the solution we came up with is pretty new. Since 2 months, we have it in Docker Desktop, and it's free for everyone. It's also open source. It's a feature called Docker Model Runner. It's basically there to provide an experience similar to Olama, using familiar Docker tooling and Docker UI. And this will run a process on the host for running the inference to give you the full speed of the Apple Silicon GPU. And most importantly, it allows pulling models from Docker Hub. So we also implemented our own format for sharing models that is compatible with the OCI artifact format that we use in Docker Hub and in other container registries, such as just as GHCR and so on. And so that means you can use your potentially existing enterprise infrastructure now to distribute and use Docker models, because like you're all probably used to having to consume and publish and distribute Docker images within your organization, and you can now use the same infrastructure to do it also for LLM models. Right, and so this is since this Docker version available on Mac, of course, because that's where we started. It's also available on Windows now, on Windows 4 CPU, which is not always super useful, right? But specifically also on NVIDIA GPUs. And we are right now pushing of releasing integration into Docker CE, into the community edition, until end of month, so that it becomes accessible also in CI/CD pipelines, single node production workloads, and so on. And once you have it available, and yeah, it's available if you have a recent version of Docker Desktop, you get this new Docker model command. And you can use it to pull models and to run models, giving you an interactive chat console. We can actually look at it. So if I do here Docker model list, you can see I have a ton of models pulled, right? And I can do Docker model run and just use any of them. Let's use a small Gemma 3 one. Okay, and like now always a stupid demo stuff, right? Just say something and it says something. Okay, yes, we see text. It's wonderful, it works. Right, so that's what we have here, but of course that is playing around, right? We want to see how we can use it in actual code integration context. All kind of popular models are available already on Docker Hub, so we redistribute them, we take them from Hugging Face, from the vendors and so on, we repackage them as OCI artifacts. You can pull them from there. We now release this week the capabilities to easily package and redistribute your own models within Docker Hub in your own organizations or within your own container registries. And yeah, that's how the custom OCI artifact specification we are working on looks like. So the thing is, packaging models as Docker images is technically possible, but also technically very inefficient, because those Docker images are compressed and like they expect multiple layers and so on. And since you cannot really compress those model files further, it just like is very inefficient to store something in a Docker image, which is an OCI image. So using OCI artifacts is just much simpler, right? In the OCI artifact, we just specify, okay, which files will be in this OCI artifact. It can be some metadata, it must be mostly a license file and so on, maybe some templates. And then you have the GGUF file, which is then the actual model file. And that's how this OCI artifact format looks like. Then we have a config format that can then contain metadata, and this is the old version. The new version has much more metadata. It shows already the expected VRAM usages and so on and so on. You can find more about this on our open source repository. So we do all this Docker model runner work in the open as open source. So the model distribution part is the OCI artifact for models implementation. Model CLI is this Docker model command. Model spec is the specification for the Docker OCI artifact format, model OCI artifact format. And then we have another one, model-runner, which I forgot to add here, which is our implementation of basically wrapping Llama CPP as the inference engine to then execute inference on a machine. Okay, so I have some minutes left for a demo, so we can look at some stuff and then also do some Q&A. And the demos are interesting because they like not always work. That's that's how it often is with LLMs. So, right. Okay. Let me show you the simple one that tends to not work, and then a more complex one that tends to work better. The simple one is already nice because it gives you an idea how SpringAI looks with Docker model runner and so on. All right, so it's like a super useless demo application here using SpringAI, and we have a couple of different APIs. That's an API that just takes your request, sends it to the LLM to then generate the response, returns the response, right? That is a dummy, no memory, no nothing chatbot experience you get when interacting with the LLM. This is the same, getting a streaming response, because if you use something like ChatGPT before, you see normally you're not getting the response as a single chunk rendered, right? You see how it streams the actual response. And this is the API you can use in Spring API for this. So instead of using here call, you use stream, and then you return a flux. So normal reactive Spring stuff here. And the clue is basically using this chat client, which is a SpringAI component, just dependency injected there, nothing to do. It just works, right? And then you assemble it. And then I wanted to try just a very easy example of tool calling, and that is not working well, and I will, when we see how it not works well, I will explain you why. So I now want another endpoint that can give me information about recent Formula 1 races, and the idea here is, okay, the LLM will have the training cutoff date, so it will not have the recent information, so it should call into a tool that has this information and then give me hopefully a useful answer. And so you can see I can now give my chat client here a new tool, an F1 tool. Okay, and if we look at this, it's also very nicely, easily implemented. It's just a Java object, and this Java object has a method, one or multiple, that is annotated with tool. And this description here is given to the LLM so that the LLM can then decide, oh, I want to call this tool, get more information, and so on. And then the actual implementation here is calling against this API that gives me through a JSON response the most recent race results of the Formula 1 race. So if we call this here, we see what happens. Okay, we get a big JSON response. And yeah, among other things, it contains the race winners and what was the last race. So it should somewhere say the last race was the Miami Grand Prix, right? And you will see here Oscar Piastri did win. Okay, so that is the only production code we really have here, right? This controller, this tool, and then this boilerplate starting point of a SpringAI application. Nothing is in here. Nothing is in here. So let's run it, execute it now through our tests. And here I want to show you how we wired up the test containers integration specifically. So now I'm using the new Docker model runner container that is available in test containers Java. Funnily enough, you have to here specify image of a SOCAT container. Why? Because test containers start the SOCAT container to then expose the Docker model runner inference API dynamically to your host, because by default it's only accessible to other containers. Now we are running this application here on the host, and then I just have Docker model runner here act as a proxy, so as a container proxy to get access to a model runner. It's not necessarily, so I don't have to do it like this, right? I can also do it like, it's always terrible to get, yes. Could also do the following. So there is under advanced, under better features, there's this enable Docker model runner, so I have it enabled, and I could now also say I enable host-side TCP support on a specific fixed port, right? Then I wouldn't need to actually use the test containers module in this case. I could just hardcode the URL, but I much rather take this more dynamic and dynamic portable approach, because it will also then work without changes on a Docker CE environment that will have a different way to determine the URL under which a model runner is accessible. Okay, so the current version doesn't yet have the setter to specify which model to use. The next release will have it. So in this case, you can then have this getter and just say, okay, I want to use it with this model, and then it will automatically pull the model as part of the startup in case you haven't pulled it yet. Okay, right. And then how do I wire this now up into my Spring context? I have to set the OpenAI base URL. And then the Docker model runner provides this getter, get OpenAI endpoint. You just shove it in there, and then you're good to go. And then you can configure which model to use. Now in this case, it's the pre-pulled model. And if we look at the very simple tests, they will all work very nicely. So I have here a test that just sends a request to the chat endpoint and will just get a response. Right, and I see now the containers popping up. Yeah, initially it has to now potentially load the model into memory, so that might take some seconds, and then I get an answer, right? So I got an elaborate answer on what Spring Boot is, so it kind of worked. And I at least could like integration test my whole system, right? I could see I have my SpringAI system correctly wired up, it eventually calls into an LLM, so it is not a terrible test as far as smoke tests go, right? I'm not asserting here on the context and the validity of the content, but it kind of works. We have here the same for the streaming example, and now I got cocky and wanted to have like a meaningful test, like showing behavior, how it uses a tool and then gives me information that can be asserted as correct, right? So I now wanted to have a request, what was the last F1 race of the season and who won, that gives me actually correct information in some shape or form. And if I do it, and now let's do a debug run, then we see something interesting happening. So I now send the F1 request. I see the model correctly identified. It has to do a tool call. That's why I end up here in this breakpoint. So it does now the tool call. We go further. So we get a result that looks pretty good, right? It's the JSON we saw before. So the tool call worked nice. And now I go on running. Let's see what happens. Now, many different things can happen. So I probably can see that my GPU is running on high load. Yeah, so you see my GPU is under full load, and yeah, so it's actually unclear what is happening right now, right? And eventually it will return something, and then it will return something that is the wrong information also. That's where we'll end up. So very, very not helpful what happened here. And I can tell you why this happens. So I have seen from my colleagues at Docker, the DevRel people and so on, they had basically the same example, and they used, instead of this F1 API that gives a quite big response, they used a small response that just gives the current time. And that worked very well. And I thought, okay, then why is this example not working very well? So it has to do with actually a bug or a missing feature in Docker model runner specifically. We get a very, very big JSON response now back. And the problem we have that the implementation of Docker model runner currently has a fixed context size window. And the context size is the amount of input, actually input together with output on which an LLM can operate. So it basically is not able to fully parse and reason about this very, very big JSON response. So often it just like kind of forgets that it gets it. So there are other models, it depends on which model you use, right? When I use a Gemma model, it runs into an infinity loop of always calling the tool because it always kind of forgot the answer it got. And yeah, so that just shows you have to be aware of many, many different moving parts when implementing these things. So context windows have to be right. You have to use the right model for the right job. You have to use the prompts correctly. And it's just like, just stuck here, right? So that's not a great experience. Let's look at a working example. Let me try to end this. And normally it returns at one point, right? So it's very interesting that it now get also stuck. That only happens for the Gemma models normally for me. Now, this is another example. Let me. All right. Let me open it in the browser quickly. Okay. So this demo application contains multiple pieces, and we have adoptions. So the goal of this application is there are a couple of dogs you want to adopt from an animal shelter or whatever, and it should be able to retrieve a fitting dog for you based on its RAG information, based on its database, and then call into an external service integrated through MCP that then schedules an appointment with you. So that is the overall architecture, right? And so that's why we have here two systems. The scheduling service is an MCP server. How to do an MCP server in Spring Boot? Super simple. You just have a service that is annotated with tool, and that's it. Now you have exposed potentially an MCP server here. And how do I wire this up into my SpringAI application? So we saw before that I can create a tool object and add it into my chat client. In this case, we want to connect it through MCP. So here we create an MCP client in SpringAI and just point it at the URL of my MCP server. And now it's magically connected without having to know more implementation details of it. Right, and then we have again a chat client similar to before with a system prompt. We add here the MCP tools as registered tools. Now the database part, we use Spring Data JPA to have a doc repository, just normal stuff, right? And now we have our REST controller. In this case, we are adding chat memory to it. also just using readily available abstractions, right? There is this prompt chat memory advisor. You can just shove in there. Boom, magically you got memory capabilities in your SpringAI application. Now we have the chat client, and now we want the chat client to, before calling the LLM, also look into my database if there are fitting information there. So that for this we can use a question answer advisor. That is this retrieval capability provided by SpringAI. And this question answer advisor, it's just a dependency inject. No, it's not dependency injected, sorry. It's created in the constructor using access to a vector database. This vector database is just dependency injected, and we don't have to do anything to wire this up. It kind of magically appears by setting the correct application properties, which we can see in the tests. And we're running out of time, so I'm just running this test here in the background while quickly looking at the test containers configuration. So here we see many more moving parts. So we see here a Postgres container that represents the vector database. We see this MCP server container, the scheduling service that I just wrapped into a generic container. And then we see the Docker model runner, same than before, right? And always we inject them through the dynamic property registrar capability we have in SpringAI for just like setting those properties dynamically, and how to initialize the data store. So we get this doc repository and the vector store, and we then create these. So we have the database itself that contains the information, right? And then we want to have the vectors that map to them. And for each of our docs, we then create those documents using the embedding API, insert them into the vector store, and there we go. And 2 minutes, very good. So did the test succeed? Where is it? Did the test succeed? Yes, so the test succeed. But what did the test do? Okay. Tests, adoptions, application, the test, server test. So it did a complete now request flow. So it asked my agent, do you have any neurotic docs available? And it will answer, yes, I have one. Per answer, how can he know this? So this is what I'm expecting, right? Since the test succeeded, it did actually answer this. How do I know it? If I'm looking here at my initialization, this is the dummy data I insert. So, and we have here Prancer, demonic, neurotic, man-hating animal. Looks like a gremlin. So this lookup worked correctly. So we now got this information. Then the next call is asking, when can I get an appointment? This will then lead to calling the scheduling service through via MCP, which it does, and then I get an actual number I can verify because it's hard-coded to always give you an appointment in 3 days. So it worked in this case, but sometimes this test also doesn't work, right? So everything very undeterministic, very fun, new stuff we have to get used to when developing non-deterministic systems. Cool. Okay, I kind of finished showing everything, even if it was a bit rushed. So I think we are not having time for questions and answers anymore, but you can just come to me and talk now, or maybe there are already some here.